When we set about using machine learning to train models, one thing to keep in mind is feature importance. Specifically, we want to use explainers to determine the importance of various features from the perspective of a trained model. Basically, what these explainers do is they help us to quantify the influence of individual features in the training data that was used to train a model. The importance of a feature means that it has an impact or an influence on the model's ability to predict labels. In other words, when we start training models, it's a good idea to attach explainers to our model so that we can determine the impact that each individual feature has on the model performance. So let's talk about global feature importance. Global feature importance refers to the importance of features across the entire dataset used by the model. Basically, the idea of global feature importance is to help quantify the relative importance of individual features as a whole. Now, this can actually provide a general comparison capability between features. In other words, you can see how important a feature is compared to other features in the dataset. The objective is to be able to determine how various features affect the model's ability to make predictions. So, for example, imagine you wanted to create a model that would predict whether a patient is diabetic. When you trained that model, your training dataset would include a ton of features and the labels that tell the model whether the patient is diabetic. Now imagine one of the features in the dataset is how many pregnancies the patient has had. Now imagine that the vast majority of the patients that were diabetic had numerous pregnancies, while those that weren't diabetic had one or less pregnancies. Well, from a global importance perspective, that would mean that the pregnancy feature is a very important feature indeed because it has a significant bearing on the prediction. So how exactly is a global feature importance determined? Well, it's like I said, the first thing you have to do is train a model from a dataset with known features and labels. The training exercise will evaluate the data using whatever algorithms you want to create a model. And each time you train your model, because you can train it however many times you want, you'll get a slightly different version of a model that has different accuracy, recall, or just overall performance. Now, after you've trained a model, you can then use something like an explainer to see what sort of impact each individual feature had on the prediction. You can do that by running representative datasets through the model and seeing how each feature in each data point impacts the prediction. The greater the impact a feature has on the prediction across all the data points, the higher its importance to the model. Now, besides global feature importance, we also have local feature importance. But what's that? Well, if global feature importance measures the influence of a feature across the entire dataset, local feature importance measures the influence of each feature against individual predictions. So let's take the example of a dataset of patients again. We want to evaluate that dataset and train a model to predict whether patients have diabetes. Now, our training dataset already has the answer in it. And when we determine the global feature importance, we look at how individual features impact the prediction as a whole. So we're saying that, generally speaking, the number of pregnancies a patient has had seems to be the feature that most influences the probability that a patient will have diabetes. However, if we were to look at an individual patient, we might say that in that one particular case, it was actually BMI that had the most influence on the prediction. Another patient might not have diabetes at all, and the feature that most influenced that outcome was their insulin level. Now, when we look at a feature importance for an individual data point, that's when we're talking about local feature importance. So, just how do we determine local feature importance? Well, it's not too much different from global feature importance, actually. The first thing that's done is to determine which features of a particular data point seem to have the greatest influence on the prediction made by the model for that specific data point. And each of the features of a particular data point are then assigned a local importance value. You can then rank each of these features based on their importance rating. So obviously, the higher the rating, the higher the importance. Now, it's important to understand that there are lots of different types of models, but feature importance is really only applicable to supervised learning models, and that means regression and classification. In our diabetes example, we're using a binary classification model. The patient is or is not diabetic. Now, depending on the model you use, the importance calculation can get pretty hairy. Now, the good news is that the Azure ML SDK and Python in general includes a whole bunch of packages that can make calculating all of this much easier for you. When using Azure Machine Learning, you can make use of model explainers to gather information about the trained models. These explainers can help you determine which features are most important at the global and local levels. You can pivot the data however you want to and gather insights on just how your various features are influencing your result. Now, typically, explainers are managed through code using the Azure ML SDK. And using the SDK, you can use various programming languages, typically Python, to create explainers. It's a fairly standard process of creating the explainer object, giving it the properties it needs, and then running various methods to execute the explainer and gather the various metrics it calculates. So let's dig into this a little bit. First, it's worth noting that there's actually multiple kinds of explainers. For example, the mimic explainer actually trains an explainable model to try to reproduce the output of a given model. This is called a surrogate model. Once the surrogate model has been trained, the explanation can then be given to you, and this is useful in situations where the input model is a black box. The tabular explainer is one of the more basic explainers. It assumes the input data is tabular, meaning rows and columns. It can then manipulate each of the features of the input dataset, usually the various columns, and determine which of the features has the greatest impact on the model prediction. Now, one more explainer is the PFI explainer. Permutation feature importance, or PFI, is a technique used to explain classification and regression models. Basically, this explainer works by randomly shuffling data one feature at a time and calculating how much that particular metric impacted the prediction. The PFI explainer can very quickly calculate global importance values, but it's important to note that the PFI explainer does not support local importance. Now, once you've created an instance of the explainer you want to use, you'll then have to go about writing the code that actually does the explaining. In other words, you need to initiate the calculation. The most common calculation is figuring out global importance. Now, there are a couple of methods that you can run against your explainer. The first is the simple explain global method. This method is the one that actually does the calculation. It'll evaluate the model using the algorithm dictated by your selected explainer and then calculate the importance of each of the features of your dataset. Now, once you perform the calculation, you can then call the getFeatureImportanceDictionary method. And this method returns the various feature importance values as a dictionary. The keys of the dictionary are going to be the various feature names, and the values are going to be the actual importance values. So let's say, for example, that you have a model that predicts whether patients are diabetic. The input dataset is going to be a list of patients, and the features of that dataset would include values like pregnancies, BMI, and age. Now, after you call the getFeatureImportanceDictionary method, you get back a dictionary that would have keys named pregnancy, BMI, and age, and so on. And the value associated to each key would be the importance rating for that specific feature. Okay, so that's global feature explanations, but what about local feature explanations? Well, as I said earlier, not every explainer actually supports local feature importance calculations. In fact, the Azure ML SDK only includes two explainers that calculate local importance: Mimic Explainer and Tabular Explainer. Now, regardless of which of those two explainers you use, there's a set of methods that are available that you can use to work with the explanations. The first method that you would use is the explain local method. This is very similar to the explain global method that we talked about earlier, but obviously it calculates the local explanations instead. And remember that a local explanation determines feature importance per data point, as opposed to the global explanation, which determines the feature importance for the entire dataset. Anyway, once you call the explain local method, the explainer will calculate the model's local feature importance for each data point in the dataset that was fed to the model. And after you've calculated the local importance, there's a couple of additional methods that you can call. The first method you can call is the getRankedLocalNames method. The getRankedLocalNames method works similar to the method we saw in the global calculation. This method returns a dictionary of local features ranked by importance for every item in the input dataset. But what's important to note here is that this dictionary only includes the names of the features ordered by importance. The reason is because the dictionary also includes the individual data point references. So the dictionary can only include so much information. So what about the values then? Well, that's why we have another function to call. In addition to the getRankLocalNames method, you can also call the getRankLocalValues method. And this method also returns a dictionary of local importance information, except that instead of listing the feature names, it returns the feature importance rankings themselves. And they'll be in the same order as the names method. So often you'll find yourself using both of these methods. In this demo, we're going to create an explainer for a model dataset and get ourselves ready to run an experiment against that data. The purpose of this exercise is to ultimately get to a point where we can run an experiment against a dataset and use our explainer to see what sort of information we can get from our model run. Now, before we get started, this demo assumes that you've already provisioned an instance of Azure ML and that you have access to the Azure ML Studio. If you don't, you'll need to provision one and set up a needed compute instance. All right, now let's get started. The first thing we need to do is head over to the Azure ML Studio in our browser. Perfect. Now, to run this demo, we're actually going to execute code using the Azure ML SDK. To run code in ML Studio, we need to use the Notebooks feature. So let's go ahead and click on the Notebooks item in the left-hand menu. Good. Now, what we're going to do in this demo is we're actually going to use a sample from Microsoft to run through the steps of creating a trainer. To use the sample, we first need to clone a repo from Microsoft. So, in the File List toolbar, click on the Terminal button. Perfect. Now this loads up a terminal that we can use to issue commands. So let's type a git clone command. Let's type the following: git space clone space https github.com/Microsoft with a capital M learning with a capital L /mslearn DP-100. Perfect. Now what this command does is clone the DP-100 sample repo from Microsoft into our notebook files. So let's execute this command and wait for it to complete. Excellent. Now in the file list, let's click on the refresh toolbar button in the file list. Good. Now we can see that the mslearn DP-100 folder has been added. Now we can finally access the sample. So let's open that folder and find the 14 interpret models file and then click on that file. Perfect. Now this sample from Microsoft walks through the process of creating an explainer. As you can see, there's lots of good information about what's happening here, and I highly recommend going over this in detail. But we'll gloss over a bunch of it in the interest of time. The important thing here is that we're going to train a classification model to determine whether patients from a sample dataset are diabetic or not. We'll create an explainer to look at the output of our model to see what sort of information we can derive from it. So let's get started. Let's scroll down to the first code cell. Good. Now, to use explainers, you first need to have the appropriate Python packages installed. So in this code cell, we're installing the Azure ML explainer and interpretation packages on the compute instance that we selected. So let's go ahead and install the packages by clicking the play button to the left of the code. Excellent. We now have the needed packages installed. Now let's scroll down to the next code snippet. Good. Now in order to explain anything, you first need something to explain, don't you? Well, in this code snippet, we're setting up a model. On line 11, we're importing data about our patients from a CSV file. On lines 14 to 16, we're defining the features and labels for our data. On line 19, we're splitting our dataset into a training dataset and a testing dataset. Then, on line 23, we're actually creating a classification model object and configuring it to train itself using our training dataset. On lines 26 to 28, we're actually calculating the accuracy of our model and outputting the results to the screen. And then finally, on lines 31 to 33, we're calculating the AUC and outputting that metric to the screen too. So let's go ahead and run this code block. Perfect. Our model is trained. The accuracy and the AUC are pretty close to 90%. That's not great, but not terrible. All right, now we have our model. So let's scroll down to the next code block. Okay, so what we're going to do in this code snippet is we're going to create a tabular explainer. This is a black box explainer that'll give us some various information about our tabular data. Notice that we pass in our model to the explainer on line 4. So let's go ahead and run this code snippet. Perfect. I mean, nothing really happened, but that makes sense because all we did was create the explainer. So let's use the explainer, shall we? Let's scroll down to the next code cell. Good. Now in this code cell, we're using our explainer to tell us the global importance of the features in our dataset. We do that on line 2. Basically, the global importance tells us which feature of our dataset has the most impact on the prediction our model makes. On line 5, we take the results of that determination and order them by importance. On lines 6 and 7, we print the features to the screen. So ultimately, this code block is going to tell us which features of our dataset are the most important globally. So let's run the code and see. Interesting. According to our model, pregnancies has the highest impact on whether patients are diabetic or not, followed by age and then BMI. Now let's scroll down to the next code cell. Now, in this code cell, we're using our explainer to tell us the local feature importance. Local feature importance refers to the impact that a feature had on predicting an individual data point. So for example, imagine you were looking at one patient and then determined that that patient was diabetic. The most important local feature would be the feature that most revealed whether that patient was diabetic. But we have a pretty huge data set here and we don't want to look at all the patients. So on line 2, we're limiting the explanation to just 2 patients. It's also worth noting here that we're now exploring our testing data set. There's no sense explaining local feature importance on an already examined data set. On line 5, we use our model to get our diabetic predictions for those 2 patients. Then on line 8, we create a local feature explainer against the predictions. And on lines 11 and 12, we rank the results just like we did last time. Then the rest of the code block outputs the explanations to the screen. So let's execute this code and see what we get. Cool. So here we see that the different patients have varying important features. We also show the prediction with each patient. So we can see with patient 1 that the serum insulin was the most important feature, but for patient 2, it was BMI. Perfect. So at this point, we've cloned a Microsoft repository, we've installed some needed packages, we created and ran a classification model to predict diabetes in patients, we created an explainer, and we've evaluated the feature importance for both the global and local levels. In our next demo, we'll actually create an experiment that will use an explainer to explain the results and then run through a legitimate experiment. Great job! In this demo, we're going to create an experiment in Azure ML Studio and attach an explainer to that experiment. We'll then run the experiment and explore the direct explainer outputs. Okay, so the first thing we need to do is head over to the Azure ML Studio in our browser. Perfect. Now, in our last demo, we cloned a sample repo from Microsoft. We ran through creating an explainer to look at the importance of features both at the global and local levels. And we did all that by running code snippets in the Notebooks feature. So let's head back there and continue where we left off. Let's click on the Notebooks option in the left-hand menu. Good. Now we want to get back to our sample notebook, so let's click on the 14 Interpret Model file under the MS-Learn DP-100 folder. Excellent. Now let's scroll all the way down to the Adding Explainability to a Model Training Experiment section near the middle of the page. All right, so what we're going to do in this demo is we're going to create an actual experiment in our ML workspace. In our last demo, we created a classification model and trained it on the spot. In this demo, we're going to do the same thing, but we're going to do it via an experiment. This is an important distinction because an experiment can be fed different datasets each time it's run. Then each run can be cataloged and compared within the experiment container. What we'll do in this case is attach an explainer to our model runs. So let's get to it. Let's scroll down to that first code snippet. Now in this snippet, we're connecting our compute instance to our ML workspace. Basically, this is going to authenticate us. So let's go ahead and run the snippet by clicking the play button to the left of the code. Perfect. Now, if the output asks you to authenticate, go ahead and follow the instructions to do that. Now, let's scroll down to the next code snippet. Good. Now, in this snippet, we're preparing the system for our experiment. On lines 5 and 6, we're creating a folder called Diabetes Train and Explain. Then, on line 9, we're taking a CSV file, which will be our input dataset, and putting it into that folder. Seems pretty simple, right? So let's go ahead and run this code. Perfect. We've copied our dataset to our experiment folder. Now let's scroll down to the next code snippet. Now in this snippet, we're actually creating a Python script file and putting it in our experiment folder. And you can see that on line 1 that the file will be called Diabetes Training. This file will be run by our experiment. So let's take a look at what this file does. On line 20, we get a reference to the current experiment run that this file is being run under. On line 24, we open the CSV file we put in our experiment folder. So you can see that we could technically change that file with every run if we wanted to. On lines 26 to 30, we define the features and labels of our dataset. On line 37, we train the model with our training dataset. And on lines 40 to 47, we calculate the accuracy and the AUC metrics and log them as run metrics. Then on lines 49 to 51, we output the results of our model. And finally, on lines 54 to 59, we create a tabular explainer for our model. We run it against our testing dataset and then use a client to upload the results. Wow, that's a lot. So let's finally run this snippet. Perfect. We've created the script file. Now let's scroll down to the next code snippet. Good. Now in this snippet, we're finally creating our experiment and running our script. On lines 7 to 12, we create and prepare an environment to run our experiment in. On line 15, we reference our training file. On line 21, we create our experiment. And finally, on line 22, we execute a run for our experiment. Now it's worth noting here that we're using a run details object on line 23. That's so that we can see some information on the screen while the experiment is running. We'll also see some output when it's done too. So let's do it. Let's run this code snippet. And now we scroll down to the output. And notice that we have a script run widget in the output. This object is showing us information about the run in progress. Now this may take some time, so I'm going to save us some waiting by fast forwarding to when it's complete. Perfect! The run is complete. Now let's explore the output. If we take a look at the script run widget, we can see some properties at the top. This tells us the run ID, the time it took to run, and the accuracy in the AUC metrics that we collected. Now below the table, we actually see some information about our explainer. The feature importance chart shows us the global importance for our model. As we can see from this chart, the pregnancies feature was the most impactful on the model overall. And if we keep scrolling down, we can see additional logs and metrics about our output. Now, in our first demo, we were able to collect explainer metrics in code. Well, even though we ran our model through an experiment, we can still do that here too. So let's scroll down to the next code snippet. Now, on line 4 of this snippet, we collect the explainer from the run we just performed. On line 5, we download the explanations that were generated. And then on line 6, we specifically collect the global feature importances. The rest of the code block outputs the results to the screen. So this code snippet should output the exact same metrics we just saw in the chart from earlier. So let's run the code snippet and see. Nice! So once again, we're seeing that pregnancies are the most important feature. So that's it. We've successfully created an experiment that trains a classification model to determine if patients are diabetic. We also successfully attached an explainer to our experiment run, and we collected and displayed the explanations from our model. Great job! In this demo, we're going to use the Azure ML Studio user interface to explore explanations that were generated with our experiment run from our previous demo. Alright, so the first thing we need to do is head back to our Azure ML Studio instance in our browser. Perfect. So, like I said, in the last couple of demos, we used explainers to look at the output from some model runs. In the first demo, we used the ML SDK to train a model and then used an explainer to review the outputs right there in our code. In the next demo, we used an experiment to execute the model training. We even attached an explainer to the experiment run. We were still able to use code to view some of the output from our explainer, even when it was run through an experiment. But what if we want to visualize the results from our explainer? What if we don't necessarily want to run code to look at what the explainer came up with? Well, fortunately, ML Studio has a feature just for you. So let's go ahead and explore that. Now, as I said, our second demo trained a model via an experiment run. So we need to go look at that experiment. So let's start by clicking on the Experiments option in the left-hand menu. Perfect. Now this screen shows us a list of all the experiments that have been associated to this ML workspace. In my case here, I've only got the one experiment. The experiment about trying to determine whether patients are diabetic or not. Anyway, let's go ahead and click on that experiment. Good. Now in this screen, we're seeing all kinds of metrics about our experiment. In the top left, we see various statuses. So in our case, we see that there's only been one run and that it completed successfully. In the top right, we see a chart that graphs the AUC metric of each run. Of course, it's a bit anticlimactic because there's only been one run. And we see a similar chart for the accuracy metric at the bottom of the screen. Really interested in here is our experiment runs, and that's because that's where our explainer was attached. So let's scroll down to the very bottom of the screen. Perfect. Here we see our list of runs, and of course we only have the one run, so let's go ahead and click on it. Excellent. So now we see a bunch of information about this run. We see the properties on the left, and we see the metrics we collected on the bottom right. Along the top, there's a bunch of tabs with additional information about this run. And notice that one of the tabs is called Explanations. So let's go ahead and click on that tab. Cool. Now we see a list of all the explainers we added to our run. We can have as many explainers as we want. In our case, we only attached a single tabular explainer, so let's go ahead and click on the ID in the explainer list on the left. Good. And now we're finally seeing our explanations visualized. You can see along the top that there are a few different tabs that we can use to look at our explanations in a variety of different contexts. The first tab, Model Performance, helps us to see the effectiveness of our model based on the distributions of our predictions. Meanwhile, if we click on the Dataset Explorer tab, we can see some really cool data. Let's scroll down so that we can see the chart a bit better. Good. Now, in the right-hand side, let's choose the Individual Data Points radio button. Perfect. Now let's look at what this chart is telling us. What's most important to us here is the y-axis and the color of the dots on the chart. Yellow dots show us patients that were determined to be diabetic. Blue dots show us patients that were determined not to be diabetic, and the y-axis tells us how many pregnancies each patient has had. Now, looking at this chart, you can plainly see that patients that have had more than one pregnancy are much more likely to have diabetes. There are clearly exceptions to that, but machine learning is all about probabilities, isn't it? Anyway, this chart tells us that pregnancies is an important feature. But is it the only important feature? Well, let's click on the pregnancies label on the y-axis. Good. Now, in the Select Feature pull-down, let's choose BMI. And now let's click Select at the bottom of the panel. Good. Now the chart updates once again, and we see patients shown all over the chart. Now, if we look near the bottom of the chart, we can see that people with low BMI tend not to have diabetes, while people with higher BMI tend to have diabetes. There's clearly more of a mix here than with pregnancies, so we can tell visually that pregnancies is likely a more important feature. But let's not just take a visual glance as the answer. We want to know which feature is the most important. So let's scroll up and click on the Aggregate Feature Importance tab. Perfect. Now let's scroll down to see the whole chart. Now what we're seeing here is the top 4 most important features. And remember, a feature is considered important if it has an impact on the prediction. The higher the impact, the more important the feature. Looking at this chart, we can see that pregnancies really was the most important feature, but BMI was actually only the 3rd most important. Now let's see some cool data. Let's click on the pregnancies bar in the chart. Good. Now let's scroll down to the bottom of the page. Good. Now in this chart, we're seeing how this feature impacted the prediction. Let me explain. In this chart, the x-axis is the total number of pregnancies in the entire dataset. Some people had no pregnancies, while others had up to 14. The y-axis represents the probability that each patient has not been diabetic. The higher the number, the more likely the patient was not diabetic. So in the first column, we see all the patients that had 0 pregnancies. And as we can tell from where the dots lined up, there was a high probability that patients that had never been pregnant would not be diabetic. Meanwhile, if we look at patients that had 5 pregnancies, we can see that the dots line up on the negative side of the y-axis. And this implies that patients that had 5 pregnancies were unlikely to not be diabetic. So there it is. That's how we can visualize explainers in ML Studio. If a model was trained using an experiment, you can then view that experiment, the individual runs, and then the explanations associated to those runs. You can use the UI to view and pivot your data in a variety of ways to give you insights into how your model is performing. Great job! When you're performing any sort of machine learning and training your models, one of the things you really have to watch out for is bias. But what's bias? Well, bias exists in your model if one or more features exert more influence on the outcome than they should. Now, with bias, what we really want to do is determine the fairness of the features in the trained model. While there are definitely going to be features that play a major role in a prediction, that influence can't be an unfair weight. The ideal situation is that we should train our models using only the most necessary characteristics. So let me give you an example. Imagine you are training a classification model to determine if patients are diabetic. In the input dataset, you're given all sorts of information about the patients. Then let's say the model determines a clear correlation between age and whether someone has diabetes. If the age then becomes the major factor in how your model determines whether a patient is diabetic, then your model has bias. An extreme real-life example would be having a patient walk into a doctor's office, and once the doctor hears the patient is 60 years old, the doctor immediately provides a diagnosis that the patient is diabetic. Well, that's no good, right? Now, to determine bias, you start by measuring prediction disparity. And what's disparity? Well, imagine our diabetes example again. So let's say that 25% of people under 50 are diabetic, and 40% of people over 50 are diabetic. In that case, there's a disparity of 15% between those two groups. Now, once you've calculated the disparity, you can compare predictions between those groups to determine if there's any bias. In our case, there's a clear bias that age plays a role whether someone is diabetic. Now, some of that we know ahead of time. We call features like that sensitive features, and we need to assess sensitive features so that we can split them into different data sets and potentially evaluate them separately. In our example, we may have a model that's used for diagnosing people under 50 and a different model for diagnosing people over 50. Now, that'd be a bit extreme, but you can see one way of dealing with bias right there. But how do you know where the disparity even comes into play? Well, one way to do that is to create groups within your sensitive features, like splitting patients by over or under 50, and then comparing your model's selection rate. In our example, where 25% of people under 50 were diagnosed as diabetic, the selection rate for that group is 25%. You can then compare that selection rate to determine bias, just like we did. At the end of the day, determining bias is done by measuring fairness of the individual features. It's critically important to understand that you can't really measure things like bias and fairness unless you're performing supervised training. Remember that with supervised training, you're telling the model what the answer should be while you're performing the training. And that means that the model is trying to match your answer through its algorithms. Now, once the model is trained, you'll naturally evaluate its predictive performance. Now, how good was it at predicting the correct answer? And you'll generally do that with a testing data set that also has the known answers. Now, once you have a model with acceptable predictive performance, you can then apply a bias metric based on your sensitive features. If you have too much bias on some of your features, you'll tweak your model to reduce that bias and retrain your model. And that has the potential impact of reducing your model's predictive accuracy, but yet be much more fair. So your job is to make sure that you have balance between your fairness and your accuracy. Of course, lots of things can influence disparity. For example, if you have an uneven representation in your data, you can create bias. For example, if our input diabetes dataset included a lot of women and virtually no men, and then the men that were in that dataset tended not to have diabetes, our trained model might create a bias that assumes that men don't get diabetes, which is simply untrue. Another potential source of disparity can come from unexpected correlations. So let's imagine our diabetes dataset again, and let's imagine that it included information about where someone lives. Then, as we trained our model, we found that people that live in a particular part of the world tended to have a higher likelihood of having diabetes. Now, that might be very interesting information and worth looking into, but correlation is not causation. After all, you wouldn't be able to say things like living in Springfield causes diabetes. Good or bad, that unexpected correlation can cause disparity in your data. And one more potential source of disparity can come from an unconscious bias in the input dataset. Basically, the idea behind this disparity is that the data that was gathered was done with an unintended bias. So let me give you an example. In World War II, Britain evaluated the bullet holes in planes when they came back from Germany. Their intent was to improve the planes to protect the pilots. Now, at first glance, that seems like a good idea, but there was some unconscious bias there. The problem wasn't the planes that came back. They worked fine. The problem was the planes that didn't come back. So the input dataset wasn't very useful. Okay, so we can agree that bias can potentially cause problems in a model. So how do we go about reducing the risk of bias? Well, one thing we can do is play with the balance between the training and validation data. By applying oversampling or undersampling techniques and rerunning the training a few times, we can improve algorithms. Of course, at the end of the day, you're still playing with the same dataset, so this can only take you so far. Another option is to add more features to the mix. For example, in our diabetes dataset, we determined that age was a big factor. Well, what if we included some additional features like blood sugar and blood pressure? Suddenly, the model might see how those features influence the outcome, and so the bias towards age is reduced. Of course, we can go the other way and reduce the number of features in total. By performing the model analysis based on just a few of the important features, perhaps we reduce the bias on some features by increasing the bias of others. And finally, you can simply sacrifice the overall performance of your model for sensitive feature groups. In other words, maybe something like age really should be a bias on your model. Your recall and precision rates might go down, but if you're accurate, maybe that's good enough. When calculating bias and fairness in a model, you can use various code packages to do that. Now, one package you can use is Fairlearn. The Fairlearn package is an open source Python package that you can install on your compute target. Now, once you have the package installed, you can use it to analyze your models to assess them for fairness. You can even use it to observe and mitigate unfairness issues. Now, with Fairlearn, you can assess the disparity between different groups of data and features and make judgments or adjustments based on those observations. This is generally done by calculating metrics for multiple models to determine which groups of data and features impact the model the most. Now, importantly, the evaluations are typically always done against features that you deem to be sensitive. So you'll have to know ahead of time which features you consider to be sensitive. So let's dig into Fairlearn a bit more. First, let's talk about how Fairlearn works. Now, Fairlearn works by calculating group metrics for the features that you deem to be sensitive. The API is really quite extensive, so there's lots of ways to explore those metrics. Now, just as an example, in a binary classification model, you'll probably start by looking at selection rates because that can tell you which groups of data tend to have more bias. So, imagine a model that predicts whether patients have diabetes. You could actually group your data by the sensitive age feature so that one group includes people under 50 and the other group contains people over 50. People that the model determines to be a diabetic would be considered selected. So if 25% of the people under 50 were determined to be diabetic and 40% of the people over 50 were predicted to be diabetic, then your model would have a 25% selection rate for the under 50s and a 40% selection rate for the over 50s. And then the difference is considered to be a disparity. Now, the metrics that are calculated by Fairlearn are actually based on the standard scikit-learn model evaluation metrics. So Fairlearn will actually produce metrics based on the standard accuracy, precision, and recall metrics. So now let's say you've calculated these metrics and disparities with the Fairlearn package, and you've determined that there's bias or unfairness in the model. Well, you can actually use the same library to help reduce that unfairness. The Fairlearn package includes unfairness mitigation support through the use of various built-in algorithms that can create alternative models that take the various metrics into account. And there are three main algorithms that you can use. First is the exponentiated gradient algorithm. With this algorithm, a viable trade-off between overall predictive performance and disparity is applied. So in other words, we might choose to reduce the performance of our model in order to reduce the disparity between our sensitive groups. Next is the grid search algorithm, and this is actually a simpler version of the previous algorithm. It's effectively the same thing, but it's designed to work more efficiently with a smaller amount of constraints. And finally, there's the threshold optimizer algorithm. This algorithm performs a post-processing technique on your model and applies various constraints to an existing classifier. The idea is that the prediction result is actually transformed right as the prediction is made, and only if needed. Now, in order to use the various algorithms that we just talked about, there are rules that have to be applied to those algorithms. And these rules are called constraints because they're supposed to help reduce unfairness. Now, there are several different constraints that you can implement. For example, the demographic parity constraint can be used with any of the algorithms to minimize disparity in the selection rates. For example, in our diabetes dataset, we might want to try to ensure that the selection rate between ages are the same. Of course, in that case, probably wouldn't make much sense, but that's what this constraint is for. The false positive rate parity constraint could be used to minimize disparity in the false positive rates for certain sensitive features. Specifically, this constraint tries to make sure that the false positive rates are the same across the various groups. The error rate parity constraint works the same as the other constraints by trying to make sure that the error rates are the same across the various sensitivity groups. And the same goes for the true positive rate parity constraint too. Again, the idea is to make sure that the true positive rates are the same across groups. Meanwhile, the equalized odds constraint is generally used in combination with the true positive and false positive rate constraints. It makes sure that all the rates are the same across all the groups. In other words, this constraint tries to even the odds of getting a false positive versus a true positive, but across all the sensitivity groups. And finally, we have the bounded group loss constraint. This constraint attempts to restrict the loss for each sensitive feature group, and generally this constraint is used explicitly with regression models where loss is actually calculated. Alright, so all that sounds good, but how do we go about mitigating unfairness in our models exactly? Well, the most common approach starts with training multiple models, and that's important. Every time you train a model, you'll get a different result. Ideally, you train the model with different data sets, or at least different subsets of a data set. And with each new model, you'll get different metrics. You're hunting for the model that gives you the most accurate results. Now, once you have the various models, the next step is to compare them to each other. Specifically, you'll compare their performance, their selection rates for certain sensitive features, and the disparity between different groups. And once again, they'll all be different. And it's that difference that's key. What you're going to want to do is evaluate the predictive performance of each of your models as well as their fairness metrics. You're looking for the model that has the best trade-off between performance and fairness. Now finally, let's talk about how Fairlearn integrates with Azure ML. Now first of all, you can execute the Fairlearn package using code in Azure ML's notebooks. You can even embed them in experiments if you want to. The point of Fairlearn is to generate metrics for you that you can use to make determinations on the fairness of your model. With Fairlearn and the Azure ML SDK, you can actually pass the generated metrics off to Azure ML Studio. And these can be viewed in notebooks, or you can embed them as metrics in an experiment run. And once the data has been collected and attached to those runs, you can use Azure ML Studio to share the information with colleagues. And this can include simply viewing the metrics attached to experiment runs, or it can even include an external feature UI dashboard. Let's explore that in a demo, shall we? In this demo, we're going to explore and detect the fairness of a trained model. To do that, we're going to use a Microsoft sample to walk through how we can detect unfairness and how to possibly mitigate that. Okay, so as usual, and one more time, let's head over to the ML Studio in our browser. Perfect. Now what we want to do is use a Microsoft sample notebook to walk through a scenario where we can detect unfairness in a trained model and potentially mitigate that unfairness. So let's get started. Let's click on the Notebooks option in the left-hand menu. Perfect. Now in the file list, let's dig into the MSLearn DP-100 folder and choose the 15 Detect Unfairness file. Excellent. Now, this sample from Microsoft walks through the process of detecting unfairness in a model. It has lots of good text and explanations for what's going on, and I highly recommend reading that. However, in the interest of time, we're going to go over this fairly quickly. So let's start by scrolling down to the first code cell. Now in this code cell, we're installing the Azure ML SDK's fairness package onto our compute instance. We'll need that to determine fairness. So let's go ahead and run this code cell by clicking on the play button to the left of the code. Good. Now let's scroll down to the next code snippet. Now in this snippet, we're installing another set of package. So let's go ahead and run that. Now it might take some time, so I'm going to fast forward to when it's complete. Good. Now let's scroll down to the next code snippet. Now, in this code snippet, we're actually going to train a model. On line 8, we're using a file with diabetic patient data. On lines 11 and 12, we're defining the labels and features for the file. On lines 15 and 17, we're creating an object that groups the data into two sensitivity data groups, patients over 50 and patients under 50. Here we're defining age as a sensitive feature, and we're going to check those two groups for bias. On line 20, we split the data into a training dataset and a testing dataset, but we also keep a random subset of the data to use for our bias check. Then, finally, on line 24, we train our model. So let's go ahead and run this code cell and train our model. Perfect. Our model's trained, and we've split our datasets accordingly. Now let's scroll down to the next code snippet. Good. Now in this snippet, we're collecting the metrics about how our model did. The important part for us here is all the way down on line 27. In this command, we collect some metrics specifically related to the column we want to test for bias, the age column. So let's run this command and see what sort of metrics we get. Good. Now at the top of the output, we see the overall metrics for the model itself. At the bottom of the output, we see those same metrics, but as they relate to our two age groups. Now, based on these metrics, we can see from the selection rate that a larger proportion of our patients are seen as diabetic if they're over 50. And that means that we have some disparity between selection rates. The accuracy is pretty equal between the two groups, which is expected, but the recall and precision aren't very close. And that indicates that there's maybe some bias in how the model makes predictions for each age group, because these particular metrics should be more or less the same. But looking at these raw numbers isn't so fun. It's easier if we have some visualization. So let's scroll down to the next code block. Now in this code cell, we're creating a feature dashboard so that we can look at the numbers more easily. So let's run this code cell. Good. Now in the output, we see that a link to a dashboard has been rendered. Now it doesn't really work so well, the actual dashboard, in this interface, so let's click on the link. Good. Now we're taken to another tab in our browser where we're going to be walked through our results. So let's go ahead and click on the Get Started button. Good. Now on the first screen, we see that the dashboard has correctly seen that we've chosen age as a sensitive feature and that we've created two age groups. So let's click on Next. Now we're being asked to select a metric that we want to compare. Now in the previous code snippet, the recall wasn't so great. So let's select that metric and click Next. Now we're being asked to choose the comparison we want to view. Well, let's go with the default demographic parity difference and click Next. Perfect. Now notice that the stats here are pretty much the same as what we saw in the previous output. Importantly, we can see that the recall metric in the first column and the two age groups are not aligning very well. And we'll get back to this. So let's close this tab. All right, so let's scroll to the next code snippet. Now in this code snippet, we're going to exclude the age feature and then retrain the model. We're going to pretend that it has too much of an impact on the prediction, so we're going to take it out completely. So you can see we remove age from the list of features on lines 2 and 3, and then we create some new data sets on line 7, and we train a new model on line 11. So let's run this code and see what happens. All right, so once again, we get a link to the feature dashboard. So let's click on it. And let's select the same configuration as we did last time. Get started, age sensitive, recall, demographic parity difference. Perfect. Now notice that our recall is a bit better this time. It's still not bang on, but we've certainly reduced the bias by removing the age column. Of course, that can make our predictions worse now since we know that age is actually a factor. So how do we deal with that then? Well, let's start by closing this tab. Let's scroll down to the next code snippet. Now in this snippet, we're actually registering our model, so let's just go ahead and run that. Good. And now let's move on to the next snippet. Now, this snippet uses the Fairlearn package to create a binary classification group metric for our model. We're actually creating an experiment in this code snippet, and I won't go into too much detail here. Let's just run the code block. All right, and now let's scroll down to the next code snippet. Now this code cell runs the experiment, so let's do that. Now let's scroll down to the next code block. Now the question is here, how do we mitigate unfairness? Ultimately, you want to balance the predictive performance of your model with the fairness of features. You don't want any individual feature to dominate the prediction. Otherwise, you'd simply say to everyone over 50 that walks into a doctor's office, congratulations, you have diabetes. So what we do in this code snippet is we use the grid search algorithm to try to force our model to even out the bias on our sensitive features, in this case, the age of the patient. On line 8, we create a grid search object and associate it to a decision tree classifier model trainer. On line 12, we pass in the training dataset that we created, as well as telling it what our sensitive features are, in this case, just the age. On lines 23 to 28, we create a loop that iterates over as many models that are needed by the grid search object and make predictions. We output a few bits of information to the screen in the process. So let's go ahead and run this. Awesome. So now we see a few models were trained and run. So let's scroll down to the next code snippet. Now, in this code snippet, we're once again going to open the Fairness dashboard. So let's run this code snippet and then click on the link when it finishes. And let's go through the same process as we did last time. Perfect. Now notice that this time we're getting a chart that shows us all the parity differences over the recall rate. Now what we want is a low disparity, but a high recall rate. With low disparity, we're saying that there's no real difference between the recall rates between the two age groups. And with recall, we're saying that our model is performing well. So the ideal model appears in the bottom right corner of this chart. In this case, we know that age really is a big factor in determining diabetes. So it's going to be unlikely that we'll get a model right in that bottom right corner. But if we did, we'd select that model as our best model. If we learned something about the age feature in this demo, it's that it really is an important feature and it shouldn't be removed from the model. At any rate, that's one way to go about mitigating bias in your model. Ultimately, the idea is simply to play with your data, remove features, re-add them, test models multiple times with and without those features. Some features will have a big impact and perhaps they need to stay. Some won't have an impact at all and can be safely removed. If you get really fancy, you can even look into normalization to reduce bias further. Anyway, we've successfully run through how to detect bias and even options for mitigating that bias, all with the ML SDK. Great job! So in this course, we've examined model feature bias and differential privacy. We did this by exploring global and local features of machine learning, how model explainers are created using the Azure Machine Learning SDK, creating an explainer and uploading an explanation, using Azure Machine Learning Studio visualizations to visualize models, using Python to generate explanations, machine learning model bias, and detecting and mitigating model fairness using the Fairlearn Python package. In our next course, we'll move on to examine machine learning model monitoring.